Hello, class. So my name is Tyler Maley. I'm mathematics faculty at Marion Technical College, and I'm making some instructional videos for you, so you don't go behind in content with Carl out this week. So I'm going to cover 2.8 and 2.9. um, all right, so we'll go ahead and get started with the Explore. So with the Explore problem on 2.8. I guess just kind of a side note, I would urge you to, follow along in your book and take notes as you would in class. I'm approaching this more of a lecture style. Granted, we can't do group work, or at least can't do group work as easily online, asynchronously. Um, so I'm approaching this if I were teaching this class online, and I noted in the class window also that if you feel comfortable with learning in this type of environment, you'll get kind of a taste of an online math class with me through this video. You can feel free to sign up for quantitative reasoning or statistics that I teach both of those online as well. Alright, so go ahead and get started here. So with Explore, so it says consider the following sequence of figures. How many squares will be there in the nth figure? Explain how you wrote your expression based on the physical pattern in the figures. Right. So we're looking at these three figures. So we're given figure 1, figure 3, and figure 5, and we're trying to see how are these related. So trying to figure out a pattern here, right? So we have some experience with pattern recognition from some previous sections. So one way I might start looking at this is let's just look at these in three different ways. So we have horizontal bars here, right? And then we also have horizontal ones here and here. And then from that, I'll use a different color. We have ones that are going down, right? So like in this spot, there's 0 of them, right? They're going down. But then here, I have 2 of them going down. And then when I get to figure 5, I have, 4 of them going down. And then I'll get a different color. So we'll get black here. And then we also have these part of the figures that are going upward from the horizontal part. Right, so in order to recognize this pattern, that was the important part, was to kind of look at this as those three parts, right? So then now we need to try to think of a way to express this in terms of n, right? Where n is the number of figure, right? So n equals the number of figure. So you might have to use just some reasoning to try to figure this out. So if we consider just the green, right, we can think about, well, how is 1 related to the number in the horizontal part here, right? So so in other words, here n is 1, here n is 3, and here n is 5, right? So I'm trying to think, how does this n value relate to the number of boxes that I have here, right? So I have 4 boxes going this way. So maybe it's possible that this horizontal part, right, is n plus 3, right? So in order to know if it works or not, I need to see if it applies to my other 2 figures, right? So if without counting those, if the expression is n plus 3, then when n is 3, we would have 3 plus 3, which is 6, right? So do I have 6 in the part that's horizontal? So I have 1, 2, 3, 4, 5, 6, right? So that seems to check out here. So we can check out the next one. So if n is 5, then I would guess that there should be 8 boxes here, right? 5 plus 3. So n plus 3, which is 8. So I can count 1, 2, 3, 4, 5, 6, 7, 8, right? So that seems to hold true, right? So I know that I'm going to have with the horizontal part, I'm going to have n plus 3 number of figures, right? Number of squares. So then now I need to try to think about maybe look at the part that's going upward, right? So these squares. So when n is 1, I have 1 block here, right? When n is 3, I have 1, 2, 3 blocks. When n is 5, I have 1, 2, 3, 4, 5, right? So that would tell me that this horizontal part, it appears to be that n is there, right? So the part, the grouping of squares that go up, it appears that this is just n blocks, right? So then now we have to consider this part in red, right? So let me go ahead and change my ink. So this part in red, part that's going down, we need to try to figure out a pattern to know how many blocks we have here, right? So when n is 1, I have 0. When n is 3, I have 2 of them, right? 1, 2. When n is 5, I have 1, 2, 3, 4, right? So it appears that this is n minus 1, right? The part that's going down. Right, so whatever n is, we subtract 1 from it, and that is how many of those squares are showing up. So then what we're trying to do, right, how many squares will there be in the nth figure, right? So we want to know total how many squares there will be. So if I add this up, right, to find the total, right, so I have 1, 2, 3 n, and then plus 3 minus 1 gives me plus 2, right? So this would be my total, 3n plus 2. So if I ask you, you know, how many blocks will figure 16 have, right? We could figure it out by plugging in n equals 16 into my formula, right? So 3 times 16 plus 2, right, is what, 50? Right, 3 times 16 is 48, right, plus 2, we get 50. So without having to draw this figure, I can use this equation to figure out what, you know, whichever figure that I would like. All right. Alright, so now with the Discover, right, there's just some reading here. So it says, if you compare answers in the Explorer with other students, you'll likely realize that they saw the situation differently than you did, right? So you may have approached this problem and saw it differently than the way I saw it, right? I saw it as these 3 kind of distinct groups, right? But there's only, you know, one way to know if we're both correct, and that is if this final simplified answer is the same, right? So this simplified expression that we got 3n plus 2. So if you're doing it correctly, as I am, a different way, as long as you can get down to 3n plus 2, then you would know that we were both we would both have an equivalent answer, right? So this is the final expression of the number of squares should match yours if they're both correct, right? So in order to compare your expression, you need to be able to simplify them. In this section, you will get more practice using the commutative, associative, and distributive properties to simplify expressions, right? So these 3 properties are real helpful in order for us to simplify algebraic expressions. So kind of our 2 guiding questions that we're going to be looking for in this section is, how can you tell if expressions are equivalent, right? And then also, how can you decide if your way of modeling a situation is equivalent to someone else's, right? Alright, so this next part is looking at, suppose we are planning an event that will require renting tables and chairs. The tables are to be arranged in one line with the sides of the tables touching and chairs placed on all available sides. We will assume the tables are square and could fit 1 chair on each side. The first few arrangements are shown here, right? So, so here, if we have 1 table, here's if we have 2 tables and 3 tables and so forth, right? And trying to figure out a way to determine, well, how many chairs can I have if I have, you know, X number of tables, right? Or N number of tables. So following this kind of diagram, we're trying to fill in this table. So it says complete the following table by determining how many chairs can be accompanied for each number of tables and write an expression for n tables, right? So what I would do is we can first, begin just playing around with the pattern. So if we have one table, we would be in this scenario, right? One table. So then I can begin to think, well, how many chairs can I fit around, right? So remember the rule here is that we can fit one chair on each side, right? So I can fit one chair here, here, and here, right? So with one table, I can only have four chairs, right? So then, like in this case, if I have two tables, right? So here, these are my number of tables. Then I can have 1, 2, 3, 4, 5, 6, right? I can end up having 6 total chairs. Right, so now we can look at what if I have 3 tables, right? So I have 1, 2, 3, 4, 5, 6, 7, 8, right? So I would have 8 total for 3 tables, right? So for 4 tables, we don't have something like that drawn, but if you wanted to, if you still didn't see the pattern, we could certainly draw 4 more, right? So here's 4 tables, so I can have 1, 2, 3, 4, 5, 6, 7, 8, and then 9, 10. Right, so I can have 10 total tables. So the next would be 20. So at this point, with the first 4, hopefully you can start to see kind of a pattern based on the number of tables, how many chairs we can have, right? Because drawing 20 tables or 200 tables can become hard to compute, right? So really, after you solve number 4, we need to begin to start to think about n. So then I can use my equation to find, well, what happens if I have 20 tables or 200 tables, right? So what you'll notice, like in this case here, n is 4, right? So what you'll notice is if I have 4 tables lined up, I can fit 4 tables on this side, right, or 4 chairs on this side, right? Because each of these sides is from one table. And then I can also do this on the opposite side, right? So these two people looking at each other, right? I can also fit chairs along this side, right? So far I have like 2 times n, if you will, right? But then I'm always adding in 2 more to come up with these end tables, right? Like the head of the table, the two main ends, right? And you can see that's true for 3 tables also, right? Notice I have 1, 2, 3 here, and then 4, 5, 6, right? So that's essentially 2n, right? I have 3 tables. If I double it, I will come up with these values, 6. And then I need to add in 2 because I need to pick up these 2 spots at the head of the table, right? So basically, I'm getting 2n plus 2 for n number of tables. So now I can begin to find, well, what happens if I have 20, right? So if I have 20 tables, right, I can just plug this in my formula. So I would have 2 times 20 plus 2. So this gives me 40 plus 2, which is 42, right? So we can have 42 tables, or 42 chairs with 20 tables, right? So now we need to look at what happens if I have 200 tables, right? So I could have 2 times 200, right, plus 2. So this would give me 400 plus 2, which is 402. Right, so I can have 402 chairs. Right, so now I can begin, to think about, however many tables I need, how many chairs I can fill in there, right? So the next, this part of the reading, we can look at that there are 4 different ways you can think about having looking at this pattern, right? So I'll let you read those on your own, but you'll notice in a minute that all of these are the same, right? There are 4 different ways to think about it, but we end up with the same answer in the end, right? So in other words, when we simplify the algebraic expressions, they're all equal to one another, right? So then here, here it's just saying what I just said, right? So it says each expression in the table can be simplified to help us determine if they're equivalent, right? So we can look at these, we can simplify them and see if they're equivalent. And remember that when things are equivalent in mathematics, they're equal to one another, right? 4 quarters is equivalent to $1, right? That's equivalence. Their amounts are equal, right? We can swap them with each other and they're exactly the same. So here we have just a note here that we have some common phrases and the corresponding expression, right? So these are just different phrases you might see like in word problems or in mathematical problems, and then what it means in terms of algebraic, right? So for example, twice a number is 2n, right? Half a number is n over 2, right? 2 more than a number means n plus 2, right? So you can read those, and you want to be familiar with these expressions, right? If you aren't already. All right, so now we're on page 212. So we're going to look at simplifying these expressions, number 3, and determining if they're equivalent. Right. So let me make this text a little bigger. Oops, I need to pull this down now. Alright, I think we're set now. Sorry about that. Alright, so I just want to simplify each part here and just see if I get the same thing for all of them. So for part A, right? So one thing I can do to simplify is I can distribute this minus 2 through. Right, so what I'll get is 4n minus 2n times n plus negative 2 times negative 1. Right, so this gives me 4n minus 2n plus 2, which gives me 2n plus 2. Right, good. So part B, n plus 2. So I just need to combine my like terms. So I have n and n. So 1n plus 1n is 2n, and then I have plus 2. Right, there's nothing I can do with the plus 2. It doesn't have a like term. So then here, part C, I need to distribute the 2 through. So this gives me 2n minus 4 plus, and then 2 times 3 is 6. So then now I can combine these two terms that are like, right? So negative 4 plus 6. So this ends up giving me 2n plus 2, right? So far, these are all equivalent, right, to each other, right? So we can look at part D and hope that we get something that's equivalent also. So we get 4 plus, right? And this is still distributive property, right? So generically speaking, distributive property is where we have A times B plus C, and this equals AB plus AC, right? But we also have the commutative property, which says that I can change the order of factors around, right? So if I have B plus C in parentheses times A, these are equivalent to each other, right? So this would still be AB plus AC, right? So if you have a factor on the outside that's on the right, it's the same thing as on the left, right? May not be as commonly written that way. We might get a little used to seeing distributive property look like this, where you have the factor on the left, but of the single factor term on the left, but it's still the same thing, right? So if this bothers you, I could rewrite this as 2 times n minus 1, right? So I can just swap these two factors around, right, using the commutative property of multiplication. And then I can go ahead and distribute. So this would give me 4 plus, so 2 times n is 2n, and then 2 times negative 1 gives me minus 2, right? So then I have this term and this term that are like. So 4 minus 2 is 2, so I'm left with 2n plus 2, right, yet again. So all four of these, when I simplify them down all the way, then I got the same expression, right? So they're equivalent. Right. And simplifying in mathematics, right? The way I kind of think of it is you're trying to write it with the least amount, using like the least amount of ink, right? Or like if you're typing it like on the computer, you want to push the least amount of buttons, right? That's probably the maybe the easiest way to think about it, right? So you just want to keep going until you can make it as simple as possible, right? So we just got a blurb to read in the text. So it says it's interesting to note that there were several correct ways to count the number of chairs, right? But each method resulted in the same expression. We can try the same approach with a different configuration of tables and chairs, right? So basically what the author is saying here is that it's interesting to think about that, given the same problem, someone could think about it four, totally different ways, but it still be correct, right? So that just reminds us that, there's different ways to look at a mathematical problem, and one way we can check to see if we're all on the same page at least is to simplify our equations or our approaches and see if we can get equivalent statements, right, to one another. Right, so like number 4 here says, let's consider another way of arranging the tables and chairs we just discussed, right? So instead of arranging them in a row as before, we're arranging them in this plus sign, right? So it says use the following table to record how many tables there are of each type. Then use that information to write an expression for the number of chairs, right? So we have to think about this table and these expressions and how they're related, right? So the table is trying to prompt us for this. So initially what we're trying to figure out are how many chairs can we get if I have n tables, right? So just as a reminder, I'll write down that n equals the number of tables. Right? So like here in this case, I have 1, 2, 3, 4, 5 tables, so n is 5 here. Right? And with this one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Did I miscount that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Nope, 9. Right? Yeah, that makes sense. So then now I need to count the number of tables I have here, right? And I guess maybe even easier way to count is I have 1, 2, 3 here, and then I have 3 along each spoke, right? So I have 4 of those. So here we'd have 3 times 4 plus 1, right? So I would have 13, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Alright, so now let's try to fill in the table. So it says the number of tables with 0 chairs, right? So we're looking at our diagrams and how many tables will we have that has 0 chairs, right? Well, the ones that have 0 chairs are this table in the center that kind of gets blocked on all 4 sides, right? So it can't possibly have a chair. So the number of tables with a chair, we're always going to have one table with this configuration, right? And as long as we're altering it and keeping this pattern, we're always going to end up with one table in the direct middle that can't use a chair, right? And then now we're looking at, well, how many tables can have one chair, right? So in other words, in order for a table to have one chair, I'd want a table that there would only be one side to put a chair, right? So like here I can put a chair, but maybe this is blocked here and here and here. So the other three sides would have to be blocked in order for me to have a number of tables with one chair. So if I kind of look at this pattern, right? So like in this first configuration with 5 tables, we don't have anything that would fit in with just one chair, right? They all have at least two or more sides available, right? Besides the one in the center is 0, right? So if we look at like n equals 9, right, same thing, right? So this one has 3 sides available, right? 1, 2, 3. Here I have right, so maybe this will be easier. So here, I only have 2 sides available, right? So this one's 3, 3, 3, and then 3, right? And this one's 2, 2, 2, 2, and 2, right? So in other words, I'm using this to show my two chairs, right? And I'll use the green highlighter to show for 3. Right, so and keeping that, I'll do the same thing here with this figure, right? So then if I look at this next figure, the ones with 3 are always going to be these ones on the end, right? And then the ones that fit 2 are these guys, right? So in looking at that, I don't have any options for number of tables with one chair, right? So I'll put a 0. And then how many tables do we have with 2 chairs, right? So let's try to see if we can find a pattern. So when n is 5, I have 0 of these, right? So maybe make a table. So here we'll put n, and here I'll put number of 2 chairs, right? Number of tables with 2 chairs. So if n is 5, we don't have any. Excuse me. So I don't have any with the pink color, right? So this would be 0. When I have 9, I have 1, 2, 3, 4, right? There's 4. And then with n equals 13, I have 1, 2, 3, 4, 5, 6, 7, 8. Right? So we need to try to see if I can see a pattern, right, between the connection of number of tables with 2 chairs and n. So if you notice, if I take 5 minus 5, I get 0, right? If I take 9 minus 5, I get 4. And if I take 13 minus 5, I get 8. So in other words, to find the number of tables that have 2 chairs, I can just take n minus 5. Right, so if this is n, then I can take n minus 5 to get that, right? So that would go here, n minus 5. And then we can look at, well, what's the number of tables with 3 chairs, right? So if we keep going in this pattern, we're always going to have 4, right? It's not dependent on n. It's always going to be these n points, no matter how many tables I put in between, right? So now we're looking at what's the unsimplified expression for the total number of chairs, right? So we need to go through and count, right? So if I have one table that has 0 chairs, right? So I'd have 1 times 0 chairs. And then number of tables with 1 chair, I would have 0 times 1, right? And then number of tables with 2 chairs, I have n minus 5 tables with 2 chairs. And then I have 4 tables with 3 chairs. So this breaks it up for 0, 1, 2, and 3. 3 number of tables with that many chairs, right? So if I take the number of tables I have times the number of chairs I'll fit on that table, then this expression tells me the whole amount of chairs I can fit around, right, based on n. So now we can simplify, right? So what happens is these first 2 terms just cancel out, right? I'd have 0 plus 0 plus, and then I need to distribute. So I would get 2n minus So 2 times minus 5 minus 10, and then 4 times 3, right, I get plus 12. And then I can simplify this further, right? So 0 plus 0, we can just ignore that, right? So then I would get 2n, and then negative 10 plus 12, we get plus 2, right? So 2n plus 2. Right, so and actually I think this was right the same as what we had before, right? 2n plus 2. Right, good. So just to make a note, right, that's just a coincidence. It's that's not always going to be the case, right? If I give you a problem where there's a different configuration with tables, this isn't always going to be the expression, right? So you want to keep that in mind, that that's not always true. All right. Excuse me. So now let's look at the example here that's in the book. So here it says your neighbor is building onto his square patio. He plans to add 5 linear feet to both the width and the length of the patio. He claims that the patio will then be 25 square feet larger. How do you know he's incorrect, right? So we don't know what the original patio length is, right? So what the book is saying, and if you're a visual learner like I am, right? So let's just draw this. So we have this generic square patio, and I don't know the dimensions. So if I don't know something, right, I can just use a variable, right, to think about it. So we can think of this as an x by x patio, right? The length and width both equal x. And then what we're doing is we're adding feet to the width and the length and trying to see how this changes my area, right? So currently the area of this figure is x times x, which is x squared. Right? So that's my original area, and see, do we have a name? It just says your neighbor. So our neighbor is claiming that we're only adding on 25 square feet, right? So let's think about this a little bit, right? So if I have my original patio, that's x by x, right? This is x, and this is x. Then if I'm adding 5 feet to the length, right? So maybe call this the length. Here would be 5 additional feet, right? And then I'm also adding in 5 feet this way. Right, so this is 5 feet as well. Right, so this is 5, this is 5. And we can break this down this way if you want. So this is x feet, this is x feet, this is 5, this is x. Right, this is x. Right. So now we can find the total area of this figure, right? So let me draw this a little better. I was just trying to draw it with these extensions so you could see what would happen. But what you're gonna end up doing is you're still gonna have a square where each side measures x plus 5. But it's gonna end up split in 4 pieces like this, right? Where this is x, 5, x, 5, 5, x, 5x, right? Each piece. So then I can find the area of each individual part and then add it up, right? So this part here will be x by x, right? So x squared area, right? X times x. This one will be 5 times x, so this will be 5x area in here. This area will be 5 times x, so 5x. And this area, this last area, is 5 times 5, which is 25. So if I add up all these individual areas, it will equal the total area. So that will give me x squared plus, so 5x plus 5x, we get 10x, and then plus 25, right? So add up all of these, combine like terms, and this is what we get. So this is my new area, right? So if we compare it to the old area of x squared, right? We're not simply only adding plus 25 onto it, right? Excuse me. We're also adding this 10x part to the area as well, right? And that's what the solution is trying to walk you through, right? So the author approached it more from an algebraic point of view, and I try to supplement that with doing it with the visual way, right? So depending on which way you prefer to learn, right, you could pay attention to my visual piece, or if you're stronger with reading, you know, if you prefer that way, then you could read that on your own, right? But so the important thing to note is we don't get equivalent areas, so therefore they're not the same, right? So in other words, x squared plus 25 is not the same thing as x squared plus 10x plus 25. Right. So then the last problem here, number 5, which is the connect, says which of the following expressions are equivalent if an expression has no match, right? Two equivalent expressions for it, right? So in other words, we want to simplify simplify these as much as we can and determine if it's equivalent to another expression that we have in this list, right? All right. So to save space, I'm gonna go ahead and delete this wrap up part. Right, so you can read that on your own, right? It's just meant to reflect and just think about what we learned and how it all connects, right? We want to, you should be asking yourself, you know, to go back and think of those 2 questions and see if you can answer those okay. All right, so try and make that a little easier to read. All right, so let me grab some ink. So part A, there's nothing we can do to simplify this, right? Everything, every term is simplified, and none of my terms are like terms. So there's nothing I can do with part A, right? Part B, so immediately you should be thinking I can distribute, right? Distribute this 2 through here, and here I can distribute the negative 2 through, and then we can combine like terms, right? So what I would end up getting, so 2 times 2x squared is 4x squared. And then 2 times negative 2x is minus 4x. And then 2 times negative 1 gives me minus 2, right? So now I need to distribute the negative 2 through, right? And it's real important to note that this is negative 2, right? And if you have trouble with that, one thing we can do is you can rewrite it as plus minus 2, right? If that helps you remember. So this value here is really minus 2, and we're going to distribute it through, right? So what this would give me is minus 2x squared plus, right? Negative times negative is plus, so plus 4x. And then negative 2 times 3 gives me minus 6. So I can go ahead and combine like terms. So I have minus 4x with plus 4x. So that'll actually cancel out, right? Make that 0. And then I have 4x squared and minus 2x squared. So this will give me 2x squared, right, combining these 2. And then I have negative 2 minus 6, I get minus 8. Right? So maybe I'll just write this beside b, so we get 2x squared minus 8. Right, for this part B. So in part C, we have something similar going on, right, where I need to distribute and then combine like terms, right? In fact, that's kind of the gist for a number of these, almost all of these. So we'll distribute the 2 through, the 3 through, and then this negative sign through. So we can think of this as a negative 1, right, in front. So what this will give me is 4x minus 2 plus, so 3 times x squared is 3x squared. And then 3 times negative 2x is minus 6x. Right? Oops, let me rewrite that. So now I need to distribute the negative 1 through, so I would get minus x squared plus 2x minus 6. Right? So then we can combine like terms. So I like to start with the highest degree polynomials first, right? The biggest exponent. So I have 3x squared and minus x squared, right? So those are my only x squared. So 3 minus 1 gives me 2x squared. So we get 2x squared. Right, so I took care of those. And then worry about maybe my degree 1, right, or my exponent of 1 for x. So I have 4x minus 6x. So that currently I'm at negative 2x, and then I have plus 2x. So those end up canceling each other out, right? So 4x minus 6x plus 2x goes away. And then I have negative 2 minus 6, which gives me negative 8, minus 8. So right now I have part B and part C being equivalent to one another, right? So I'll just make a note of this, right? So currently part B and C are equivalent. So then we'll look through part D. So part D, I'm just going to distribute this 2 through. So this gives me 2x squared. 2 times negative 4 would be minus 8x. And then 2 times plus 7 would be plus 14. Right. So here I get 2x squared minus 8x plus 14. Right. So in here I could do the same thing. Right. We need to combine like terms. And really, you know, these parentheses aren't doing anything. Right, so we don't really have to worry about them because I can use the associative property here and the commutative property and like rearrange everything and put like things beside each other, right? So there's nothing really to do here besides combine like terms. So I have x squared and x squared. So this gives me 2x squared. Then I have negative 2x and minus 2x. So I get minus 4x. And then negative 2 plus 9 gives me plus 7, right? So we get 2x squared minus 4x plus 7. And then here with this one, part F, you know, you can think of this as a plus, and then I have a negative 1 in front. So I need to distribute the negative 1 through. So what this is going to do is just change all my signs. So instead of negative x squared, this will be x squared. Instead of plus 3x, this will be minus 3x, right? Instead of minus 6, this will be plus 6. So then I can combine like terms. So I have x and x squared gives me 2x squared. Negative x minus 3x gives me minus 4x. And then 1 plus 6 gives me plus 7. Right, so I get 2x squared minus 4x plus 7. Right, so what we end up with is that A, E, and F are also equivalent, right? So I have B plus C, which were equivalent, and also A, E, and F are equivalent to each other, right? Because when we simplify them, they're equal. So we picked on A, B, C, E, and F. So we skipped over D, right? So D was this lonely person, didn't get matched up with someone, so we were asked to write 2 equivalent expressions for it, right? So you could, you know, do anything you wanted, right? You could make this as simple or complex as you want. So if I want something to be equal to 2x squared minus, where we were at part D, right? Yeah, part D. So if I want something to equal 2x squared minus 8x plus 14, right? Something easy that you could do is we could say, oh, let's add 5 and then subtract 5 away, right? So if you add a number and then subtract that number away, these will, in essence, you're adding 0 to the expression, right? So this is equivalent to part D, right? So you could do something as basic as that, or you could maybe you wanted to do something like part F, where we're subtracting two polynomials, right? So maybe in this first one you want to put 4x squared, right? So then what would I have to take away from 4x squared to get the 2x squared, right? So I would need to take away 2 of them, so I would need 2x squared here. And then you could put, I don't know, plus 24x here. So then you're thinking to yourself, so 24 minus what gives me negative 8. Right, so 24x minus what gives me negative 8x, right? Because I want this term to result. Right? So if I so if you subtract 28x from both sides, we're left with well, instead of the question mark, let me use like the variable. We'll just use a, right? So if I take 28x from both sides, what I end up with is negative a equals negative what was that, 36x. So then a would be positive 36x. So that's what I need here. I would need a plus 36x, right? And then we want plus 14, so you could even just put plus 14 here, and then we could just have nothing here. And so this would be another equivalent statement, another equivalent expression to part D, right? So there's multiple different answers you could have there, right? The important part to check your work is if you simplify each of those, you should get 2x squared minus 8x plus 14. All right, well that ends lesson 2.8. So I'll go ahead and stop that video, and feel free to email me with any questions that you have. maleyt@mtc.edu. So I put that in the announcement, or you can also find me on the Marion Tech website. My contact information is also, if you go to www.mtc.edu/mathematics, that'll launch you to our Math Changes website, and my contact information is the first one on the left there. All right.